In this video, we're going to talk about one of the applications of derivatives called related rates. But before we talk about related rates, let's review the concept of implicit differentiation. Okay, let's say we have x. What's the derivative of x with respect to x? According to the differentiation rules, this is equal to 1, right? Now, why is it equal to 1? This might seem obvious, but it's because we are taking the derivative of x with respect to x, and this simplifies to 1, right? This is perhaps the simplest way we can make sense of this derivative. Another way is through the use of the limit definition of the derivative and applying the delta process of finding the derivative, but we are not gonna discuss that approach here. Now, how about x cubed? What's the derivative of x cubed with respect to x? Using the power rule, this is 3x squared, right? But this is actually 3x squared dx over dx. Again, this is because we are taking the derivative of x with respect to x. And again, this simplifies to 1. Okay? Now, what if we have y? What's the derivative of y with respect to x? This is equal to dy dx, right? And but if we have y cubed, what's the derivative of y cubed with respect to x? Applying the same concept, you have 3y squared dy dx. Okay? What I'm trying to point out here is that it's very important that we know with respect to what variable we are differentiating. Okay? Because for example, if we take the derivative of x with respect to y, this is not 1 anymore. It becomes dx dy. Same with y. If we take the derivative of y with respect to y, then it will not be dy dx. It becomes dy dy, or that's 1, right? And that's the concept of implicit differentiation. Okay, we can take the derivative of an equation or a function with respect to another variable or with respect to another parameter. In the case of related rates, we differentiate with respect to time. Okay, so we'll be dealing with rates at which quantities change over time. Okay, say for example you throw a pebble into the water, creating circular ripples. These ripples will get bigger and bigger over time, right? And as they get bigger and bigger over time, we have some quantities that change over time. Area will change over time, right? The radius of a single ripple will change over time. And we can relate these two quantities, hence related rates, okay, using an equation or a formula. And since we assumed that the ripples are circular in shape, we can relate these two using the formula for the area of a circle. Okay, again, hence why we call them related rates. Now, to determine how these two quantities change over time, we can take the derivative or differentiate this equation with respect to time. Okay? So we have to apply implicit differentiation. So taking the derivative of the area with respect to time, this is equal to pi times uh, derivative of r squared with respect to time, that's 2 times r dr dt. Okay. Another approach in taking the derivative, okay, is through the use of chain rule. All right. So initially we have a equals pi r squared. We only have a and r. We can actually differentiate this equation with respect to r, right? So that you get pi or 2 pi r, and then you have dr over dr. And then we apply chain rule, right? So we multiply both sides by dr dt. Okay, so we can simplify this equation, cancel out dr, we get dA dt equals 2 pi r dr dt. Okay, so this is using the chain rule. All right. Depending on the problem, the change in the area with respect to time can be known or unknown. The change in the radius also with respect to time can be known or unknown, and our task is to solve for whatever is unknown in the given problem. Okay? So to solve related rates, we have some guidelines. Number 1, just like with optimization problems, we can make a sketch of uh, the system or the situation being described in the problem. Okay, the sketch will help us in setting up the working equation for the problem, because it will give us an idea on how the unknown quantities are related to the known quantities through some formulas like area formula, volume formula, or some other formulas that can be derived from mathematical facts like similar polygons or similar solids, or the Pythagorean theorem from right triangles, so on, so forth. Okay. Okay, very important when sketching the graph. We should put labels. Okay. In other words, we should define some quantities. For quantities that will not change over time, or quantities that are fixed, then we substitute the values or the constants. Okay. For quantities that will change over time, we label them as variables. Okay. So remember, when quantities change over time, regardless if there is a given value, we should not put the value immediately. We should label that quantity as a variable. Okay. Next, we set up an equation. Again, this will be based on whatever is being described in the problem. Okay. So equation for formulas for area, volume, so on and so forth. Next, we differentiate the equation with respect to time. Okay. And then lastly, we solve for the required quantity. Alright, so let's solve some problems. Oil from an uncapped well is radiating outward in the form of a circular film on the surface of the water. If the radius of the circle is increasing at the rate of 1.5 feet per minute, how fast is the area of the oil film growing at the instant when the radius is 300 feet? Okay, the oil film is circular in shape, so let's draw a circle. And then we have some given quantities. Radius, let's call the radius r, and it's constantly increasing at the rate of 1.5 feet per minute, so let's call that dr. dt, and this is equivalent to 1.5 feet per minute. Okay, so the radius is r. Notice that I did not immediately put 300 feet for the radius. Okay, remember I mentioned earlier that for quantities that will change over time, we label them as variables. Okay, and according to the problem, the radius will increase, okay, over time. However, we can only substitute this value 300 feet later on after we differentiate, or after the differentiation process. Okay, also we have some sign conventions for the rates. Okay, if a quantity is increasing over time, then its rate is a positive value. Okay, if the rate is decreasing, then the value is negative. Okay, alright, since the system being described is a circle, therefore our working equation is the formula for the area of a circle. Okay, and then we are asked to find how fast the area of the oil film is growing at the instant when the radius is 300 feet. So what we want is the rate of change of the area over time, that's dA over dt, at the instant. So we have a condition when the radius, or r, is 300 feet. Okay, let's solve using the formula for the area of a circle. A equals pi r squared. Take the derivative with respect to time, so dA dt equals pi r squared. Pi is a constant, so we apply the constant multiple rule. Then we have r squared, apply the power rule, bring down 2 pi r, and since we are differentiating with respect to time, don't forget the factor dr dt. Okay, before we continue, imagine if we immediately put 300 feet for the radius. The working equation becomes a equals pi r squared, where r is 300 feet. Okay, and then taking the derivative with respect to time, the right side of the equation, this is squared, right? The right side of the equation becomes 0. Okay, and it does not make sense for the problem because we know that the area is increasing over time. Therefore, there is a change. If the value is 0, meaning there's no change at all, right? And it does not make sense for the problem. Okay, so let's continue. Let's plug in the values. We don't know dA dt. That's what we are after. So 2 pi, the radius is, so we can now plug in the value for the radius, the dr dt, the change in the radius per time, so 1.5. This is equal to 900 pi, or that's approximately 2827.43. And then the unit, so we have area over time. A unit of length in the problem is feet, so square feet per unit time. Unit is minutes, or minute.